Okay, so today we're going to look at section 2.3, continuity and the intermediate value theorem. Okay, so let's take a look at what we got going on here. What does it mean to say that a function is continuous? To answer this, we need to first define continuity at a point. So here's our definition, continuity at a point. You want to make sure we know this one. It is used on the AP exam in making sure that all three of these little steps are satisfied. So, continuity at a point, a function f is continuous at x equals c if, okay, these three conditions are met. And when you are asked to determine if continuity exists, you have to show and establish all three of these steps. So it's very, very important to do so. Step number one, is f of c defined? So if I come over here in my graph, at c, there should be a dot somewhere at c, so that there is a value for y. It may not be nice on here, so if it's not on the curve itself, then it will not be continuous. But the first step is to establish that there is indeed a point there. It can't be a vertical asymptote, it can't be a hole in the graph or anything like that. There's got to be a point. The next thing we have to determine is that the limit exists there. So we already talked about limits. So as I approach c from the right, am I approaching a value? It does not have to be f of c to be for this limit to exist. Okay, and as I approach c from the left, do I approach a value? Okay, so there has to be the same value, has to be a limit, has to exist there. And the final thing is the limit has to actually be the point, f of c. So if that occurs, then we indeed have a continuous, have continuity at a point. Okay, so that's important to establish all three of these things. If a function is not continuous at point c, we say that f is discontinuous at c, and that c is a point of discontinuity of the function. So you can see how they're going to categorize and reference this scenario. A function is continuous on an interval if and only if it is continuous at every point in the interval. Okay. A continuous function is one that is continuous at every point of its domain. Okay? Not every point on the number line, but every point in its domain. If it's every point in its domain is the function is continuous, then we have a continuous function. And this is how you deal with the trig functions that have vertical asymptotes. Because the vertical asymptote is not in its domain, the function can be considered continuous on its domain. And we'll look at that in more detail. So here is our reciprocal function. Let me just go ahead and move this up and so you can see it. Here's the 1 over x. The domain is all the real numbers. X cannot equal 0. In interval notation, it would look like this. Okay. This function, 1 over x, is not continuous on the interval from negative infinity to positive infinity. There is a point of discontinuity at x equals 0. There is a vertical asymptote here. Okay? This is not continuous on any interval that contains x equals 0. Okay? But 1 over x, f of x equals 1 over x, is a continuous function because x equals 0 is not in its domain. It is a continuous on its domain. So since 0 is not in the domain of this function, see it's not there, then we can say that this is a continuous function on its domain. But any interval that I choose that contains 0, it would not be continuous on that interval. So that's how the definitions kind of work there. The following functions are continuous at every point on their domains. And so I gave you some examples here. Show you down here so you can see them. Polynomials, radicals, exponentials, logs, rationals, and trigonometric, they have vertical asymptotes, maybe sometimes more than one, occur at x values not in their domains. So that's why these are all continuous functions on their domains. Here's some examples of functions not continuous on their domains. This function right here is an example of one that is, the domain is all the real numbers. Every x value has a y value, okay? But it's not continuous because look right here, we have a hole and a dot is off of that line. So it does not satisfy continuity at a point because the limit does not match the value of the function. Here's another one. This is a step function, the domain of which is all real numbers, okay? But yeah, you can see there's multiple spots where they would not be continuous. Again, not satisfying the continuity at a point. The limit from the left does not match the limit from the right, so the limit does not exist. Here's some more on this other side. These are types of discontinuities you want to be familiar with, because when they ask questions, you're going to be looking for these things right here. Types of discontinuities. This one right here and this one right here are what are called removable discontinuities because they only have a hole in the graph. And removable basically means this. If I redefine a point to be that hole, then it will become a continuous function. That's why it's called removable, because you can redefine a single point. Whereas these over here cannot do that. These are, and the different names for them. This is what's called a jump discontinuity. This one is not continuous. It fails the limit. This is an infinite discontinuity. Again, the limit does not exist as I approach this value. It's going upwards without bound. And the oscillating discontinuity. The closer and closer I get to zero, the more this graph goes up and down, back and forth, back and forth. And so it's impossible for it to settle in on a single number, so the limit here would not exist. And this is called an oscillating discontinuity. So we want to be familiar with these types of discontinuities. So when we see them again, we'll know that they exist and we can identify it. So I have an example now I want to look at that we're going to be doing of establishing the kind of problems you're going to be asked to do. So just this one up here, and then we'll do the next one. Here is a function. We can see that it is a piecewise function. Let f be a function defined. Okay. For what value of k is f continuous at x equals 3? So we have to go through all three criteria to establish this. So the first thing I have to do is, what is the value at f of 3? Is there a value? So when x equals 3, the value is whatever k is. The next step is we have to do the limit. What is the limit as x approaches 3 from the left of this function? And I'm just going to write that for now. And we have to find out what the limit is as x approaches 3 from the right. Well, in both cases, it's this piece right here for everything that's not 3. So whether I approach 3 from the left or approach 3 from the right, it's going to be this function right here. So that is what we're going to write as x approaches 3 from the left of x squared minus 9, x squared minus 3x. And this is the limit as x approaches 3 from the right of the same function. So let's do the top one, and we'll use our factoring technique and all that stuff to modify this, because if you plug in 3 on the bottom, you're going to get 3 squared minus 3 squared is going to be 0. So we cannot do that. We can't plug in. So I'm going to factor and see if I can't reduce some things. So the top's going to become x plus 3, x minus 3. The bottom's going to become x times x minus 3. So we can see that these will reduce out, giving me a function that is equivalent to this right here of x plus 3 divided by x, for which I can plug in 3. And I'm going to get 6 over 3, which is going to give me a 2. Which means doing the same thing over here produces exactly the same material here. And so this will also be 2. so it satisfies the fact that the limit as x approaches 3 of this function is 2, so the limit does indeed exist. So the last step here is to do what? Okay. The last step is to establish what k has to be so that this becomes continuous at this point, which means this limit as x approaches 3 of f of x has to be equal to f of 3. So this right here is 2, this right here is k, so k has to equal 2. And so that's how you can establish part 3. Okay? Same thing here. So f is defined as this right here. If this limit exists and f is continuous on the entire number line, what does k have to equal? Find k. So if that's the case, then we can go through this entire process right here. And the limit exists means that the limit as x approaches 4 from the left of this function, okay, is going to equal the limit as x approaches 4 from the right of the same function. So we know those two things are going to be equal. So let's go ahead and figure out what each one of these individual ones are. When x is less than 4, this is to the left, and so this is going to be the limit as x approaches 4 from the left of x squared minus k. And then if I'm coming from the right, then we're on this function right here, as x approaches 4 from the right of negative 3x plus 18. So we work each of these out, okay? Nothing here is going to give me some 0 over 0 kind of thing, the indeterminate form. So if I can probably directly plug in 4, so this is going to give me 4 squared minus k, or 16 minus k. Same thing down here, I can plug directly in 4. So negative 3 times 4 plus 18. And then this gives me a number of 6. And so because this limit exists, so because the limit as x approaches 4 of f of x exists, then I know that 16 minus k must equal 6. And then I can solve for k here and get 10. So this is how you use your definitions and what everything stands for to help solve for a problem. So you look at each individual problem individually, ask, what is it telling me? What do I know about something? What has to be true because of this? So because f was continuous on the entire number line, I knew that both, and this limit existed. I knew that everything here was going to match up just like this. Okay? Particularly because this limit exists, I know the limit from the right and the limit from the left must be equal. And so I found each one and then set them equal to each other. What about this one right here? Here's h. For what value of k is h continuous on its domain? Okay? So the one location that can be suspect here would be at 5. Okay? So I want this to be continuous at 5. So is there a value at 5? Yes. Okay? If I take 5 and I plug it into here, I'm going to get an h of 5. It does indeed exist. There is a value here. Okay? So it really boils down to what we're going to look at is that limit again. Does the limit exist? Okay? So you have to check here to make sure that there is a value. You can see this is going to be a calculator problem. I'll show you how you can do this here in a minute. Let's go ahead and do our limit as x approaches 5 from the left. And that would be, we're on this piece right here. And then what is the limit as x approaches 5 from the right? And that means we're on this piece right here. And we can work each one of these individual pieces out. So the only thing we can do here, I don't know what k is, but we know it's not going to be 0 on the bottom. So if I plug in 5 here, I'm going to get 12 over k to the 3 plus 5. And if I plug in 5 into this one, I'm going to get k squared minus 5. For it to be continuous on its domain, it has to be continuous at 5, which means these two pieces must agree. They have to be the same because the limit has to exist. That's how I establish my equation. I know that this must equal this for it to be continuous. So the reason why this was a calculated problem because this is a little bit more complex for us to solve individually, algebraically, and so we just use our calculator. Let me show you how I do it on our Inspire calculators. So the first thing I would do is I would graph this side, and then I would graph this side, and then look for points of intersection. So in my calculator right here, I do have a thing. I graph the first side, and I've typed in the second one. So I hit enter, and I'm going to look for points of intersection. I can see that I have one right there. Okay, so let's go through the process here of finding that point of intersection. Remember, we go over here to the menu button. We're going to analyze our graph, and we're going to look for intersection number 4. Okay, and then it's just a matter of going through this process here. The lower bound, select, upper bound, select, and there's my value right there. I can grab it. I can move it so I can see it. And there you go. What does K have to equal? K is approximately equal to 2.377. Then we round all of our answers again to 3 decimal places. Okay? So let's look at the next item on our topic, the intermediate value theorem. Okay? The intermediate value theorem is basically what the calculator just did to find that answer. Okay? So when you look for a point of intersection or a 0 or a max or a min, the calculator is using this to determine it. Okay? This is what it's doing. So here's what the intermediate value theorem says. This is also one of our existence theorems. That's why it's important. You want to know it. There's a couple of existence theorems that we use in calculus. There's 3 of them. This is the first one. If f is a continuous function on the closed interval, AB, and E is a number between f of A and f of B, then the intermediate value theorem guarantees that there is at least one number C between A and B such that f of C will be D. Okay, so what they're saying here is that if I have a continuous on a closed interval between A and B, every y value between these 2 points is going to have an x value that the function mapped to it between A and B. Okay, that's what they're saying. They're saying that there exists a number guaranteeing that C is going to exist. Every number here, going backwards to the x is between A and B. That's what this thing is saying to us. So when we made our little lines there, I was setting these boundaries right here, A and B. Okay, and then it showed me what the x value had to be to get the number that I was looking for over there, that point of intersection. Okay, so let's look at an example how we might use this. So here's an example. Let h be a function defined by this. Can the intermediate value theorem be applied to guarantee a value in this interval where h of x equals 0? Justify your answer. So we have to go through a process of justification. Okay? So how do I start a problem like this? What do I do? What am I supposed to be thinking about when I see a problem like this? Okay, well, the first thing I want to think about is, obviously, because the intermediate value theorem says that f had to be continuous on a closed interval. Here's my closed interval. The question is h continuous on this interval? Is h going to be a continuous function? So that brings us to go back to those functions that were going to be continuous, one of which was polynomials. They're always continuous. This is a polynomial, so I can say yes, because h is a polynomial, it will be continuous on here, and so that's what we can say in our justification. H of x is a polynomial and is continuous everywhere. When I say by everywhere, that means it's continuous on the entire number line from negative infinity to positive infinity. Okay? So the next thing we want to do is we want to establish our A and B, which is going to be these things right here. So A equals 1, B equals 5. And why we need to do that is because we have to make sure that we can find that H of 1 and H of 5. So we got to find those too. So what is H of 1? What is H of 5? So we plug these into H over here. They're going to get 1 cubed minus 2 times 1 squared minus 4 times 1 minus 5 equals negative 10. And then we can do this one too. So 5 cubed, 5 squared, 4, 5. And we get these numbers right there. So there's my two pieces on the side. So if I was graphing this thing, I have this one here, excuse me. There's 50, here's negative 10, and we have the establishment of 1 and 5. So I haven't even graphed that, but I'm going to be using that same kind of concept here. All right? So then what can I say from this? Is 0 between? There's my D. D is 0, right? It's in between those two. So is there an X value? So since I know that D equals 0, and I know that D equals 0 is between negative 10 and 50, we can use. So the question was, can I use the intermediate value theorem? I have a continuous function on this interval. I've established D to be between these two values, so the intermediate value theorem does indeed guarantee, okay? We can use the intermediate value theorem to guarantee that there is a value C between 1 and 5, where H of C equals 0. Okay? So that's what we have established here, and yes, we can use the intermediate value theorem. So we want to make sure that you check everything out to make sure that you can use these things out. Here's the last example we're going to look at. Selected values of f are given in this table. F is continuous on this interval right here. What is the fewest number of zeros possible? Okay, so when I'm asking the fewest number of zeros, I'm saying, do I even have zeros? Okay, and so this is a classic example where you would use the intermediate value theorem to establish that, try to find, are there zeros? This is how the calculator establishes your zeros. Okay, so what do I know here? I know that I'm given, okay, that f is continuous on this interval. I got to establish, every time I use it, I have to establish that I have all the conditions necessary to use the intermediate value theorem. So the first one is it continuous on this interval? I was given that it is continuous on that interval. I know that f of 22 equals 1, and I know that f of 24 equals negative 3. Why do I want that one? Because between a positive and a negative number, I know that there is a 0 between there. Because f of 24 which is less than 0, which is less than f of 22, I know by the intermediate value theorem there exists a C between 22 and 24 where f of C equals 0. So I know this. And if I look over here, I can see, okay, so now I'm in the negative realm, and I know, here it is again. See that switch? So I can make this exact same argument again for this interval right here. And so you can write it all out. So we have f of 28 is negative 3, and f of 30 equals 1. And because f of 28 is less than 0, which is less than f of 30, so there's the 0 between the two f values, y values, by the intermediate value theorem, there exists, and I'll use a different letter this time, a t that is between 28 and 30, where f of t will be equal to 0. So because of those two scenarios right here, I can say the fewest number of zeros is 2. Okay, so there's two examples of how we're going to be using the intermediate value theorem in class and also on the AP exam. So that concludes this video, and we'll do more questions in class.